In our previous lesson last week, no, we discussed about the Newton's laws of gravitation to be able to understand, no, the reason why, there is such a thing as a body that is falling, no, due to gravity, no. So we tried to make an explanation out of that, no, and we understand, no, that the the nature or the phenomenon called gravity is largely dependent upon masses of objects that are involved, including the distances that exist between them, no? And we see that now in this equation formulated by Newton called the law of gravitation. There are two factors that we mentioned here, and we were able to come up with an equation below that is called as F, no? And F is equals to G, which is a constant, no, universal constant, and M1, M2 is being multiplied divided by S squared. No? Now the value of G, I think, is 6.67 times 10 to the negative 11. Now that's Newton meter square per kilogram square. No? So that value, used in this equation allows us to calculate how much is the force of gravity. Now again, the more massive the body, then the greater is the gravitational force. Likewise, when you move the body further away from each other, then we also affect the value of the gravitational attraction, which lessens it by the inverse relationship of the square of the distance between the bodies. And the bodies are well, and again, we measure the value of this gravity by a unit called Newton. And again, so this is our law of gravitation. Now we need the knowledge here, for us to be able to understand, guys, the idea of a freely falling body. So a body that falls by virtue of the action of gravity, is falling down with an acceleration equivalent to 9.8 meters per second square. And the direction of this falling body is always downward. So this is a phenomenon of a body that goes directly downward. Now we were able to come up with equations last time, and we have quite a number of equations for the free falling body. Now, before we go to the equations, we were able to also identify factors that affect this gravitational acceleration. And one of them that we identified was latitude. That's how far a body is from the equator. And we believe that the Earth is not equally sized. It's more thicker on the equator than on the poles. Since the Earth is spinning, then I believe that's one effect of the spinning motion of the Earth, that the equator is much further from the center of the Earth. It's much thicker in the equator. And I would like to make a correction to the value of the gravity that is present in the equator compared to that of the poles. Since the poles are nearer the center of the Earth, it's nearer at the center of the Earth because it's again, it's an oblate spheroid, the way we describe the Earth. So it's thicker on the equator. So we believe that since the equator is much further from the center of the Earth, that there is lesser gravity in the equator. More gravitational pull probably is found on the poles. So the north and south poles will have greater degree of the gravitational acceleration probably. So I hope you got that correction. So with regards to our latitude, so there is greater gravitational pull on the poles, north and south poles, than on the equator of the Earth. So I hope we clarify. Okay, so we were able to identify equations like this one when when we simply let an object fall down, no? So for example, we held an object, there was an object held, no? And we let this object fall down, no? By virtue or by action of gravity. No? So for instance, we have this object here, no? So you hold it in your hand and then suddenly, no, you release it from your hand, then naturally it will just fall by virtue of gravity. No? Now what we would probably presume here is that this body, no, started from an initial velocity of 0. No? We did not throw it down. No? We did not throw it up. We simply let it fall from our hand, no, by holding it for a while and then releasing it. No? And again, now we will see that this object now is falling, no, by virtue of the action of gravity. And again, now since the initial velocity is 0, then therefore what remains, no, for our v sub f equation, no, when we again identified v sub f, so our v sub f equation is actually, no, equivalent to some vi, no, value plus maybe some gravitational acceleration g, no, and multiplied by t. No? And since v sub I happens to be 0 in value, no, so we cancel this, and therefore what remains is only this expression. No? So since again, no, vi is given to be 0. No? Now for the next expression, we also use here now the equation s, or distance, is equals to s vit plus 1/2. No? And then we have some value gt, and then we square this value. No? Again, if our v sub I again is 0, then we can simply cancel this one again. No? Since v sub I is 0, any number multiplied to 0 will always be 0. Therefore, 1/2 gt square is the one that remains. No? So therefore, now we were able to come up with this equation again that is equal to this. No? So again, now this is happening now because we have an object probably that is simply dropped, no, from a certain height. No? So if it is dropped, then we believe the initial velocity there to be 0. No? Okay, I hope you follow that. No? Any question?
None, sir.
Sub I is, happens to be 0, then this will be the ending equation of S, Vf. No? And we have also an equation last time that is equivalent to this one. No? We were able to come up with this. No? So it's 2as. Actually, that was 2as, no? But this time we will call it 2gs. No? G again is the equivalent of the acceleration a, and that's equals to Vf square minus some Vi square, no, value. And since again Vi happens to be 0, so we can eliminate this portion here. No? So we can make that 0. And therefore what remains is this equation. No? Okay, now to be able to solve your v sub f here, no? In this particular equation, we can exchange their location, and therefore we can place v sub f on the left side now. But since we are looking merely for v sub f, then we can write that as equivalent to 2gs, no? And we extract the square root. No? Okay, so the squared value, when you remove the squared value of vf squared, then to get v sub f, then you are to extract the square root of 2gs. Okay, do you understand that? Huh? Are you following the equation that we are deriving? Now, aside from an object that is being dropped, no, we will be provided here with a next set of equations, no, and allow me to delete all this first, no, the ones that I wrote, no. I will repeat. If we are dealing with merely an object that is being dropped, no, then we can apply this equation. No? But we will understand that free-falling body, no, free-falling body by virtue of gravity does not only happen when you drop something. No? What if you throw something downward? No? So is it still no possible that when an object is being thrown downward, no, that gravity is still acting on it? No? Question, no? Again, if a body is being thrown downward and therefore the initial velocity here, no, v sub I, is no longer equal to zero. No? So again, no, because again, no, the body is thrown down. No? So is the body still acted on by gravity? No? So again, no, we did not equate that to zero because there is now an initial velocity, because this is a body that is thrown down. No? So that's thrown downward. No? Now we will agree now that gravity is still acting on the body, except that there is now an initial value. No? So in this next instance, now, so from the equations that we wrote without v sub I, we will simply include v sub I. No? And that will be now our equation on this side. No? So this side is simply now adding a v sub I, because the v sub I value is no longer zero because you throw something downward. So the body is now much faster, no, compared to you simply held it, no, and then you let it fall down. No? Okay, so again, first we remove v sub I because we simply let it fall down. But if we include v sub I, then that is still a free-falling body. However, now we see that there is now an initial value. No? Now, what about if you throw an object up? No? Is it still acted on by gravity? No? So the object starts from the bottom, and then you now throw the body upward. No? Now, when you throw something upward, no? So bodies that are thrown upward, it cannot go up without an initial value. No? So the value of the initial velocity cannot be zero also in this case. No? But question, is the body still acted on by gravity? Do we still expect that the value of gravity is present in the body that is being thrown up?
Yes,
Okay,
sir.
so again, now, when you throw something upward, no, it is still a body that is acted on by gravity. No? So bodies that are thrown upward, no, is still a free-falling body. No? Why? Because gravity still acts on it. No? How much is the value of gravity in both instances that we are showing here? Gravity is still equals to 9.8 meters per second square. It does not change, whether it's going up, it's going down. The value of gravity is constant. Now, throwing a body upward will still be a thing of gravity, because we do not see it going out of the earth. If there's no gravity acting on it, then this body will just simply go up, and then it will never go down anymore. It will be lost in space already. But you will see that at some point, which we call as the maximum height, when you throw something up, so at the maximum height, the body, the final velocity of the body becomes zero. That's what happens when you throw it up. It will always come to a maximum height, and then it will stop moving already. So upon reaching the highest point and it stops, we will realize that the body now will behave as though it is a body that is dropped. So the same phenomenon. So the body starts to go back down because we believe that its initial velocity now is zero at the highest point, and then it starts to descend downward. So a body that is thrown upward will behave the same as a body that is simply dropped down upon reaching the maximum height. So again, in these three instances, letting it drop, throwing it down, or throwing it upward, these are all phenomenon that we call as freely falling body. Now, if you try to examine, however, our equation, there seems to be some change in how we deal with our equation here. So you notice that from positive GT square, we kind of change the equations on this end. No? Now, for our consumption, I would like to change this one so that we will not be confused anymore. No? Let's just change all of that to positive. No? And I want you to note it down. No? So all the values here will remain the same. No? From the left to the right side, we will not change our equation. No? However, what we will change is our value of gravity G, no? Which we will always assign as negative. No? So the value of G is the one that we will make negative every time. No? Okay, are you following me? So we will now make G negative 9.8. Now, we will also change the direction of S and V. No? So V is velocity and S is displacement. No? So whenever V is going up, it's going up, right? We will indicate it as a positive value. So when V again is moving upward, we will give it a sign that it is positive. When it's going down, then we will give it a negative value. So downward motion, give it a minus sign. Now the same is true for S. Our S, when we let the body go up, we will also give it a positive value. But when the body is downward, we will give it a negative value. So S and V, since they are vectors, they are affected by signs. So again, when you throw a body downward, both its V and S value are both negative. Are you following me, guys?
Yes, sir.
Okay, so please note down with this convention. Our equation is consistent from left to right. We change all of them to positive. We will deal with a single set of equation. However, our values of V and S is dependent upon it's dependent upon its direction. Okay, so we go to this example. So we will try to apply our knowledge of the free falling body. So let's try this one. So let's start with letter A. Now, an object falls from rest. So what we can probably assume here, or we can probably say that the initial velocity of the body is the one that is being provided at the very start. It started from rest, so V sub I must be 0. And another implied given is that gravity is always negative 9.8 meters per second square. Without even mentioning that it is a given, we always know that the value of gravity is like this. Now, we want to find so it is dropped from a certain height. Again, these are the conditions. So we want to know after a time of 5 seconds whether it reaches the ground or not yet. So what about if we will determine the velocity of the body? So after falling for 5 seconds, I think 5 seconds is a long period of time when something is falling down. And what we want to know at the bottom, how much is the final velocity here? So initially, the value of the initial velocity is 0. Now, if we will find this, then we know that the equation that we'll be probably applying is V sub F is equals to simply VI plus GT. So this is our working equation. So VF is equals to V sub I plus GT. Again, V sub I will simply be equals to 0. No? So since it's falling down, no? So 0 ni siya. And then our GT value, no, is the one that remains. So VF is equals to GT. Again, G being negative 9.8 will be multiplied to a time value of 5 seconds. No? And this will be our value now in for our V sub F. No? Okay, so multiplying negative 9.8 no, to 5 gives you your value negative 49 VF squared. So once the body falls from the top of our tower here, no, it will accelerate very, very fast, and upon reaching the bottom, no, you will have a value that is negative 49 meters per second. Now, why negative? No? Why is the final velocity negative? So it is because the direction is downward. No? So velocity is vector. No? So therefore, anything that goes down, no, or to the left are described as negative. No? Okay, so this is our first number. No? So our first number here, our V sub F, is equivalent to negative 49 meters per second. So that's our first answer. Okay, let's move on to, okay, so going to the next number. So how much is S? So maybe since we are provided with with a V sub I value there initially, so maybe our S is, or distance S is equals to VI T plus 1/2 our value GT square. So because we were provided with a time value earlier, that is equal to 5 seconds. So again, there are two things that are implied here. Again, if the body starts from rest, that V sub I is 0, and our G value is always equals to 9.8 meter per second square. These are the two given that are implied without even stating or writing it. Now, since our initial velocity is 0, guys, so we can cancel this out, leaving us merely with 1/2 GT square value. And therefore, our value now will have 1/2, then multiplied by negative 9.8, and then multiplied by T, which is 5, 5 seconds, and we square the value of 5. So that leaves us with a value that is also negative. You'll see that the value of S here will become negative. So we get a value that is negative 122.5 meters. And the question is, why is it negative? Since the direction is going down. So we will be consistent that displacement, when it is also going down, is also indicated as a negative value. So this is our answer for letter. And to find the distance for the 5th second, you have to subtract the distance covered for 5 seconds exactly minus the distance covered for 4 seconds. We already calculated in letter B the value of the distance for 5 seconds, which is 122. And again, when we are dealing with distance, we merely write without the negative sign, 122. So for 4 seconds, the distance is actually 78.4. So again, we can disregard the negative sign there because it is merely a distance. So therefore, the difference of the two here, 122.5 minus 78.4, gives us a value which is how much?
44.1, sir.
Again?
44.1.
44.1,
0.1, sir.
44.1 meters. Okay, so, and that gives us our answer here. So how much is our answer? Again, now our remaining value there is 60.38 meters. No? So that's how far it is still, no, from the ground. So this is a very high tower. No? Now, with what velocity will the object strike the ground? No? So maybe we are looking for, no, V sub f. This time, maybe we will use the equation 2g, no, which is negative 9.8. And our total height, no, total height is actually 600 divided by 3.28. No? This is our value now in meters. So since that is also downward, now if we consider it to be a displacement, then we are going to get the product and get the square root, no, of our answer here. No? So our answer again will be extracting its square root value. Okay, then how much is our value there? Now, if we so again, now this is our equation now because we used the last equation that we have there initially in our sets of equations. So we end up with a negative 59.88 meters per second because the direction of the motion is downward. So before we go to the next number, please get a copy of all this. Again, now we made all the equations here consistent. None of them is changed. So kindly correct them if you see that some of them are made negative on this side here, including our negative 2gs. So we will now all make it positive, same as the other equations that we have. Wait, we go to our next number now. So in as much as we would want, the examples that we give are very similar to our quiz actually. They are not as tricky as way back probably. Now this one this is a problem about a body that is being thrown up, or in this case it's a bullet that is fired up. So therefore we have here a rifle that fires the bullet. So this one, there is now an initial velocity. So g is still negative 9.8. Please remember that. Whether it goes up or down, g is always taken as a negative value. And here are the things that we are being asked to calculate. Sige, so you can get a piece of paper there. So our initial velocity again this time is no longer 0 because this is now fired upward. But we will realize that at the highest point, this bullet will stop moving and it will start to go down. So it will become a free-falling body once it reaches the maximum height. Now its gravitational acceleration is still the same. It's going up, but we assign it a negative value, negative 9.8 meters per second. So again, the things that we will be solving, we will find the final velocity of the body after 8 seconds. And likewise, we will find its height, its S value after 8 seconds as well. We have VI plus GT, that's our equation. And V sub I is 120 plus our G value, which is negative 9.8 times our time, which is 8 seconds. So this one is still going up. So V sub F after 8 seconds is only 41.6 meters per second. So initial value is 120 plus GT, which is negative 9.8 times 8 seconds. Now the height with which it goes up must be equals to BIT plus 1/2 GP square. No? So this is our equation that has been used a while ago. No? So what will be our expression here? No? So our next answer for letter B is 646.4 meters. No? So this one will not become so high now because it is slowing down. No? So the body will come to a stop eventually now after some time. No? But I think now after 8 seconds, the body has not yet reached the maximum height. So this is not yet the maximum height. No? Okay, now you will see the next other numbers. No? Okay, for our letter C, no. So I think we already calculated the distance for 8 seconds. No? So maybe what we need is the value for the 7th second only. No? For 7 seconds. No? So S7, no? So the one that we solved earlier is for 8. No? So for 7 seconds, how much will be our distance? No? So how much is the distance that is calculated there? No? Again, no? For 7 seconds, we will be able to calculate 599.9. And therefore, if we subtract the 2, no? The difference of the two values of the distances gives us the eighth, no? The distance for the 8 seconds, which is 46.5 meters. No? So this is now our final answer here, no? For letter C. No? Now, our next number is to solve for the maximum height. No? So the maximum height, we know that the maximum height can be reached when these two values, when this value is attained. No? So when V sub F becomes 0, no? When V sub F becomes 0, then that's a value that is going up. No? Then the maximum height is also attained. No? So S here, no? Can be determined by getting, no? Vf square minus V sub I square. No? And then we divide this by 2g. No? So, but of course, our Vf and V sub I values are being squared there. No? So we divide these two. And again, no? Vf is being squared. V sub I is likewise being squared. No? And since that is going upward now, reaching the highest point, then we can say that this value now becomes actually 0. No? So this one has reached a value which is 0, V sub F. So what remains is merely Vi square over 2G. No? So that's how we solve for the maximum. So again, among the features of the maximum height, Vf is 0. So we can feature our S maximum to be negative Vi square, no? Which is negative 120 square divided by 2. And then 2 is multiplied to the gravitational acceleration, negative 9.8. No? So again, negative 9.8 kaya again, gravitational acceleration is always considered negative. No? So finally, our XS max or maximum height is 734.69. So that's positive because the direction of the maximum height is also upward. No? So upon reaching the highest point, the body stops moving already and its tendency is now to go back downward. So the bullet that you fired now is not always going up. It will always go back down to the earth. No? So we are not, no, we are always reminding, no, those people who are fond of firing, no, the bullets during Christmas time, if they have a licensed gun or if they have some kind of a gun in their house, no, that they will not fire that gun, no, during New Year's Day, no, or New Year's Eve, because that bullet that goes up will always go back downward. No? Now, what if now they are firing it in an area where it is populated, and no, it will cause, no, again, harm, no, or it may kill other people. No? So it's always true that during this season, no, there's always some stray bullet that are going around, no, or are seen, no, because of this habit. Now, some people are indiscriminately firing their weapon. No? Let's see the last item. No? So let's see now the last number. So here are the other two numbers which you may try as well, guys. No? So you can practice this now, and we can see your answers there no, next time. No?